Today's autonomous AI agents can pull from multiple real-time data streams and execute complex structural outputs in seconds. Systems built on models like GPT-3 can read multi-layered text prompts, reason through specific constraints, and deliver immediate, functional solutions. This decision tree illustrates early AI's limitation: hard-coded logic. A data point travels a programmed path, but without a specific human-coded rule, it stops entirely. With zero learning capability, it repeatedly fails at that same wall, unable to adapt. That creates a vast engineering gap between a rigid machine that requires manual instruction for every single step and a fluid system that can generate original art or natural conversation. Bridging that gap took decades of targeted engineering, specifically designed to solve strict computational bottlenecks. Human programmers face a hard physical limit. We simply cannot write an explicit manual rule for every infinite variation that exists in the real world. Machine learning offered a different approach, programming machines to locate patterns. Unorganized data points cluster mathematically. These clusters are training data. We isolate characteristics, feature engineering. Finally, the system calculates a boundary, completing statistical learning. Locating those statistical patterns is the baseline action we refer to when we say an artificial system learns. By 2012, early machine learning hit a bottleneck when it tried to process highly complex human data, specifically sight and sound. Neural networks are stacked with distinct layers. A complex input shape breaks down into simple lines in the first layer, then recomposes into complex features in middle layers. The final layer outputs a matching statistical probability, achieving the 2012 breakthroughs in image and speech recognition. But successfully categorizing existing data is a different engineering challenge than generating entirely new outputs. In 2014, the introduction of generative adversarial networks, or GANs, proved AI could synthesize original material, moving beyond simple analysis of existing data. Then came 2017's transformer architecture, where every data point connects to every other point simultaneously, instead of in a single linear line. The machine processes the entire sequence in parallel, solving the natural language processing bottleneck for complex text. To power that parallel processing, engineers needed highly specific hardware. Powerful graphics processing units, or GPUs, provided the high-density computational resources required. With the processing power secured, researchers fed these models vast datasets spanning the public internet. The results compounded rapidly. The BERT model, released in 2018, followed directly by the launch of GPT-3 in 2020. By 2022, diffusion models brought highly detailed image generation to the mainstream. True generative capabilities required this exact intersection: the parallel processing of the transformer architecture, extensive computational power, and vast datasets. This split visual captures the evolutionary journey. Over several decades, rigid, hard-coded logic was systematically replaced by statistical learning, deep neural networks, and GPU-powered transformers. Engineers knocked down the distinct bottlenecks of learning, scale, and generation one by one, enabling the highly advanced multimodal systems we see emerging from 2023 onward. Generative AI is a ladder built sequentially, rung by rung. Understanding these historical rungs provides the necessary framework for anticipating the trajectory of artificial intelligence.